In this video, I'm going to show you some examples of separable differential equations with initial conditions. A differential equation is separable if we can write the differential equation in the form of f of x dx equals to g of y dy. So if we can separate x from y in this form, we say the differential equation is separable. And for solving these type of differential equations, we have to integrate from the two sides of the. And for solving these type of differential equations, we have to integrate from the left and the right side of the equation. So we can find the solution by finding these integrals. Our first example is x times e to the power of x minus y dx minus dy equals 0, and the given initial condition is y at 0 is 0. The first step is to try to write this differential equation in this form. We have to try to separate variable x from variable y. First of all, note that we can write x times e to the power of x minus y in the form of x times e to the x times e to the negative y dx minus dy equals 0. The reason that we can write e to the x minus y as e to the x times e to the negative y is that e to the x times e to the negative y is equals, because the base are the same, if we add the powers, it's again x plus negative y, which is x minus y. So this equals e to the x minus y. So we can write e to the x minus y as e to the x times e to the negative y. And the reason that we write this in this form is that we want to separate the variables x from y. The next step is to move dy to the other side of the equation. Note that we want to convert and rewrite this equation in this form. So we want to separate x from y. So we move dy to the other side of the equation as here. So we keep x times e to the x times e to the negative y dx in the left, and we move dy to the right. Now we have to bring this term to the right, and for bringing e to the negative y to the right, we can divide both sides of this equation by e to the negative y. If we divide both sides by e to the negative y, we get to x times e to the x dx is equal to dy over e to the negative y. But note that we can bring e to the negative y to numerator and make the power positive. So we can write dy over e to the negative y as e to the y dy. The other way that you can get rid of this e to the negative y here is to multiply both sides of this relation by e to the y. If you multiply left side and right side of this equation by e to the y, you can get to this expression. Now that the differential equation is in the separable form, f of x dx equals g of y dy, x and y are separated, we can find the solution by integrating left side and right side of this equation. So integral of x times e to the power of x dx equals to integral of e to the y dy. For finding the integral of x times e to the x dx, you can use the integration by parts technique. If you choose u to be x and dv to be e to the x dx, then du is dx, and from here v, if we integrate from this, integral of dv is v, and integral of e to the x is e to the x. So this integral is equal to, if you remember from integration by parts formula, this integral is equal to uv. Let me remind you the integration by parts formula. Integral of u dv is uv minus integral of v du. uv here is x times e to the x, so this equals x times e to the x minus integral of v du. v is e to the x and du is dx. Integral of e to the x dx is again e to the x. So integral of x times e to the x is x e to the x minus e to the x. So integral of left side is x times e to the x minus e to the x. And integral of e to the y is e to the y. And don't forget to add constant c to left side or right side. Because x in this equation is in the left side of the equation, I prefer to add constant c to the left side of our solution. Now here we can use our initial condition for finding the particular solution. Note that this is the general solution of this differential equation. But because we have initial condition, we can use the initial condition to find c, so we can find the particular solution of this differential equation. Based on our initial condition, the value of y at 0, when we plug in x0, the y value is also 0. So if we plug in 0 for x, we have 0 times e to the 0 minus e to the 0 plus c equals e to the 0. Note that x is 0, y value is also 0. From here, 0 times e to the 0 is 0, e to the 0 is 1. Note that here we have negative 1 plus c is 1 because e to the 0 is also 1. So from here, the value of the constant c is 2. Now if we plug in 2 for c here, we get to this particular solution, x times e to the x minus e to the x plus 2 equals e to the y. And so this is the solution of this differential equation with this initial condition. If you like to find y from here and find y in terms of x explicitly, if you don't like this implicit form, you can write your answer in this form as well. If we take ln from the both sides of this equation, y equals to ln of x times e to the x minus e to the x plus 2. So you can write your answer in this form as well. Note that again, because e to the y is equal to this expression, so y is ln of that expression. Let's do another example. 2 times xy plus x times y prime is equal to y, and the initial condition is y at e squared is 1. The first step, as usual, is to try to separate variable x and y and convert this in the form of f of x dx equals gy dy. First note that y prime is dy over dx. And by looking at this bracket, you can see that we can factor x in this bracket. So we can write this as 2 times x bracket y plus 1. Note that if we factor x from the bracket, from xy we have y, and from x we have 1. So if we factor x, we get 2x times y plus 1 times dy over dx equals y. Now if we write this in the form of 2x times y plus 1 dy is y dx, we have to bring this 2x to the denominator of dx because we want to separate x from y, and we have to bring y to the denominator of dy. So we can write this equation in the form of y plus 1 over y dy is equal to dx over 2x. Now the differential equation is in the separable form, and we can find the solution by integrating from left and right side of this equation. So we have integral of y plus 1 over y dy is equal to integral of dx over 2x. Note that for finding the integral of y plus 1 over y dy, we can write this expression as 1 plus 1 over y dy. Because if we separate y over y, we have 1, and the next term is 1 over y. So we can write y plus 1 over y as 1 plus 1 over y. If you do a common denominator here, you can back to the original expression. Now integral of 1 is y, and integral of 1 over y is ln of y. So integral of y plus 1 over y dy is y plus ln of y, and integral of dx over 2x is 1/2. We can bring 2 outside of the integral of dx over x, and integral of dx over x is ln of x. So integral of right side is 1 over 2 ln of x, and don't forget to add c to the left or right side of your equation. Usually we are adding c to the right, to the side that x is there. Now because we have this initial condition, we can use that initial condition for finding c. This is the general solution of the differential equation, but here, because we have initial condition, we can find the particular solution. Based on this condition, if we plug in e to the 2 for x, the y value is 1. So we have 1 plus ln of 1 is 1 over 2 ln of e to the 2 plus c. ln of 1 is 0. ln of e to any expression equals to the same expression. ln and exponential function are inverse of each other, so they cancel each other and eliminate. So based on this property, ln of e squared is 2. 2 times 1/2 is 1. So here we have 1 because ln of 1 is 0 equals 1. 2 times 1/2 is 1 plus c, and so c is 0. Now if we plug in 0 for c here, we get to this solution. Y plus ln of y is equal to 1/2 ln of x. So this is the solution of this differential equation. Before we do the next example, let me show you how we can write this answer in different forms. The answer was y plus ln of y equals 1/2 ln of x. Let's get rid of this 1/2 here in our answer. To get rid of 1/2 in the right side of the equation, we can multiply both sides by 2. So we have 2y plus 2 ln of y equals ln of x. Now because in this term and in this term we have ln, I want to get rid of these ln's here and here. So I raise e, the exponential function, to the power of 2y plus 2 ln of y is equal to e to the power of ln of x. Note that in general, if we have a equals b, then we can say e to the a equals e to the b. Here, this is a and this is b. So e to the a equals e to the b. Note that e to the power of ln of x, based on this property of ln, e to the ln of any expression like a equals a. So e to the ln of x is x. So this equals x. And we can write this as e to the power of 2y times e to the power of 2 ln of y. Note that we can write e to the power of 2y plus 2 ln of y as e to the 2y times e to the 2 ln of y. If we add the powers, we get to the same expression. Now, note that we can simplify this part of this expression with this property again. But before using this rule, first we have to move this 2 to the power of y. Then we can use this property. So we can write this as e to the power of 2y times e to the power of ln of y squared is x. Now e to the power of ln of y squared is y squared. So we can write this answer in the form of e to the 2y times y squared equals x. And as you can see here, this expression seems completely different than this expression that we had initially here. But actually this expression is the same as that expression. And it's up to you to leave your answer here or rewrite your answer in this form. But I highly recommend you to learn these type of operations for differential equations. Now let's do the next example. Consider this differential equation y prime equals 2x cosine squared y, and y at 0 when x is 0 equals pi over 4. And the question is, what is the limit of y, or actually y of x you can say, what is limit of our answer or solution as x goes to positive infinity? So first we have to find the y, the solution of this differential equation, the function that satisfies this differential equation, and then we have to find the limit of that solution as x goes to infinity. First, instead of y prime, we write dy over dx as usual equals 2x cosine squared y. If we bring dx to the top and we move cosine squared to the denominator of dy, we have dy over cosine squared y equals 2x dx. Now if we integrate from the left and the right side of this equation, we have integral of dy over cosine squared of y equals integral of 2x dx. Integral of dy over cosine squared of y, this integral, is actually integral of secant squared. We know that 1 over cosine is secant of y. So 1 over cosine squared that we have here is secant squared. And integral of secant squared is tangent. So integral of dy over cosine squared of y is tangent of y. And integral of 2x is 2 times x squared over 2, which is x squared. And don't forget to add c to your answer. Now we can use our initial condition for finding c. When x is 0, the y value is pi over 4. Based on our initial condition, we plug in 0 for x and we plug in pi over 4 for y. So we have tangent of pi over 4 equals 0 plus c. And from here, tangent of pi over 4 is 1, so c is 1. If we plug in 1 for c here, we can write our particular solution. So we have tangent of y equals x squared plus 1. This answer is in implicit form. If we like to find y explicitly, to get rid of tangent, we have to use tangent inverse. So y is tangent inverse of x squared plus 1. Now that we found y, we have to find the limit of this function as x goes to infinity. So we have to find limit of tangent inverse of x squared plus 1 as x goes to infinity. When x goes to infinity, x squared plus 1, because x goes to infinity, x squared plus 1 goes to infinity. And tangent inverse of infinity is pi over 2. If you remember, the graph of tangent inverse is something like this. And as x goes to infinity, the graph of this function, graph of tangent inverse of x, approaches pi over 2, as you can see here. So limit of y as x goes to infinity is pi over 2. Let's do one more example. The slope of tangent line to the curve y equals f of x at every point is double of product of length and the width of that point. So the slope of tangent line to the curve y equals f of x is double of the product of the length and the width of that point. Find the equation of f of x if it passes through the point 0, 1. The first step in this question is to find the equation of the differential equation. We know that the slope of tangent line is y prime, or dy over dx. From calculus, we know that the slope of tangent line is derivative of the function dy over dx. And based on the question, a slope of tangent line is, so it is equal to, is double of, so 2, double of product of lengths by width. So it means that a slope of tangent line is double of, which means 2 times length times width, length x and width y. So double of x times y. So dy over dx is 2xy, because it's product of lengths by width. So x times y is the product of lengths by width. So this is our differential equation. Also, we know that the solution of this differential equation passes through this point. When x is 0, y is 1, which means that y of 0 is 1. Note that this differential equation can be written in the form of a separable differential equation. So for finding the solution of this differential equation, we use the technique for separable differential equations. First, we separate y from x. If we bring this y to the denominator and if we move dx to the numerator, we can rewrite this differential equation in the form of dy over y equals 2x dx. Now for finding the solution, we can integrate from the two sides of the equation. So integral of dy over y equals integral of 2x dx. Integral of dy over y is ln of y, and integral of 2x is x squared, and don't forget to add c. So this is the solution of the differential equation. Now we can use this initial condition for finding c here. When we plug in 0 for x, the y equals 1. So we plug in 0 for x and we plug in 1 for y. So we have ln of 1 equals 0 squared plus c. ln of 1 is 0, so c from here is 0. If we plug in 0 here for c, we can write this as ln of y equals x squared. And if you like to get rid of this ln here and write y explicitly in terms of x, you can write this as y is e to the power of x squared. So this is the function that tangent line at every point to this function, the slope of tangent line at every point is double of the product of lengths by width. And also this function passes through the point 0, 1. And that's it for this video. See you in the next videos.